Oke, boleh nampak screen? The slide.
Boleh, Prof.
Okay. So today we will cover knife-based classifier. So this is one of the supervised learning method in which they use the probability in order to predict the type of class for new unseen data. And they also call this one as Bayesian classifier because they use the Bayesian theorem. So, Dr. Jekyll, I think you are familiar with this. Um, this is based on statistics. Okay. So the principle is um, if it walks like a duck, quack, quack like a duck, then it is probably a duck. So the keyword here is the probability. Okay. So if we have new unseen data, we want to look at what is the probability of having this item, new item, belong to this class, and then we also compute the probability of the new item to be this class and so on. So we will assign the label that has the highest probability. Okay, so we need to compute the probability of having each class that we have in our dataset. So this is a statistical classifier where it will perform probabilistic prediction, where it predict the class membership. Okay, the foundation is based on the Bayes theorem, and these are the two assumptions that we make for the classifier. That's why they call it naive classifier. The first one is mutually exclusive and exhaustive. The classes are mutually exclusive and exhaustive, meaning that for one item they can only have one class. One item, one class. You cannot have two classes at the same time. Yeah. And the attributes are independent given the class. So that means your features in your dataset will be independent from each other. There is no relation. So these are the assumptions that we make when we perform the Bayesian classifier. Okay, and based on the published result, they have proven this one and scales very well. Means if you apply this one for large data set, you will have a good accuracy as well. Okay, so in many applications, the relationship between attributes and the class is non-deterministic, means there could be a way to determine the relationship between these two or not. So non-deterministic means there is no guarantee. So in such a situation, we can use the statistical probability in order to determine the relationship. Okay. So in this Bayesian classifier, they use the Bayes theorem of probability for classification. So in that case, before we go into further detail, we look at the theory of probability and then the Bayes theorem. So this is just like a revision session for you all. Okay, Bayes theorem of probability. So for this one, the simple probability is defined as given M and N, where M is we define N first. If we have N event, this is the total number of events associated with a random experiment, and M of N of them are favorable on event A. So that means m out of n, it will favor even a. Okay, so this is the what we call it, the probability, okay, of having a. Okay, we also can say that if we have two events, a and b, so if they are mutually exclusive event, that means they has nothing to do with each other. You cannot have the occurrence of one precludes the occurrence of the other. So, for example, tossing a coin, this is two events. You cannot have both head and tail happening at the same time. Similar to tossing a Ludo cube, six event, the number 1 up to 6. Okay? So they are mutually exclusive. And we also have this assumption in independent event. Two events are independent if occurrence of one does not alter the occurrence of the other. So the occurrence of the second one has nothing to do with the first one. Okay. We also have this joint probability in which if we have the probability of A and B, and these are the probability of two events, then the formula that we have is the probability of A and B is equal to the addition of the probability of A and B minus the probability of A intersection with B. Okay, so we do not want to have this. So that's how we define the probability A and B of two events, because we cannot have this one together. Okay. So if A and B are mutually exclusive, that means we can never have this. So that means this is 0. And then this turned out to be a simple one, mutually exclusive. Okay. So following from there, so if we have this conditional probability, because we are looking at this, conditional. So if events are dependent, so that means one followed by the other, or given even A, what is the probability of having even B? But in this case, we are reading given even A, B, what is the probability of having even A? Okay. So over here, they state that this can be computed by having the number of even B which are favorable to A divided by number of even in B. So if we translate this one into the formula here, so this one we are looking at the number of events in B which are favorable to A. So this one follow together, and number of events favorable to B. So if we put up this formula together, we will have this. This is the formula. Okay. And this one can be changed the order. So if we have another formula like this, of course they will have the same formula as well, like this. Okay. So these two are equivalent. Okay. Now, how do we come up with this one? Is that because let me clear this one first. Okay. So since we are saying this one together, they are the same. So for us to wait. Okay. So we are saying that, okay, to replace this one, because we are saying that, okay, this is like this. So if we change this one to the other side, the probability of A, then we have this formula. So this one can be here. So we take this one to substitute the whole thing here, and then we get this. Okay? So, so that means when we have the probability of this one, A and B, so basically that is equivalent to this, where we get this one from here, or the other way around, because we can swap these two together. So having the knowledge about this, okay, so since we can form this formula, so we can always take out this formula to be on your left hand side. So when you have that one on your left hand side, we have this. Okay, if we generalize that one, this, okay, and PB is equivalent to what we have just now. Okay, so when we simplify the law of total probability, basically we are looking at the probability of having B and A union the probability of B and not having A, because we want to get the probability of B only. So this is the formula for the probability of B. Okay, so when we substitute this one below here, then we get the full one here. Okay, we replace this with the formula that we have previously from here. Okay, so how do we apply this one? How do we apply this one in the real world data set? We look at this condition. Let me erase this. So this is the formula that we'll be using, the conditional probability. So we are looking at given this feature, what is the probability of having this class? So basically we are looking at this feature. So since all the features are independent from each other, we can separate this one. We will look at this one later on. Okay. So for example, I think I missed that slide. Yeah. Okay. Okay. So we are looking at the probability of given we have uh, okay. So this is the class level that we have. Okay. So first we look at the probability of having class. In here we only have two classes. So we have the probability of no and yes. So we just compute only lah. So no we have 5/14, and then yes we have 9/14. Okay. So now we look at the feature here. So over here we are looking at, okay, given that you have this class, what is the probability of having this attribute? Okay? So basically, you compute um, the number of uh, the number of class of specific class, and then we take also the number of attribute that having this class. Okay, for example, okay, for no, given that we have play no, what is the probability of having outlook sunny? So the sunny is one. So we're looking at the play equal to no. Okay, we are looking at the play no here. So we look 1, 2, 3, 4, 5. So out of 5, how many of them having outlook equal to sunny? So 1, 2, this one no, 3, this one no. Nope. Okay. So similar to this, if we have play equal to yes, so we look at the yes. We look at the yes, and how many for the temperature we have mild. So we have temperature mild one. This is no 2, 3, 4, 4. So 4 out of 9. So the rest follow the same. So that's how we compute the probability of having outlook sunny given the play is no, and the rest follow the same. So having this knowledge, okay. So if we have a new unseen data, for example, given today is sunny, mild, humidity is normal, windy. So the question is, should we play or not? Okay. So the new unseen data here is this x. So what we want to do is, okay, given x, what is the probability of play yes? And we compare with the same thing, given x, what is the probability of play no? So we need to compute. So we decide the class label to be yes or no, depending on which one give you higher probability. Okay. So the formula that we apply just now is similar to what we have before. So we just apply this formula. And since we assume that all the attributes are independent from each other, so we can break this one into individual probability. So we take 1, 2, 3, 4. Okay, so this one you can break up into 4. So we have 4 here. 1, 2, 3, 4. And then times with this. Okay. Okay, so since we have all the x here, so we just have put the sunny, mild, normal, and windy is true. Okay, so for this one, we can ignore because for both yes and no, we will be using the same. Okay? So if we go ahead and compute the probability of um, having sunny, given that the play is yes, so we place yes, yes, yes only. So what is the probability of having sunny? So we have 1, 2, 2 only. So 2 only. So we have 2. Okay, now we go to mile again. So mile for the temperature. So we have 1, 2, 3, 4. 4 only. So 4. So we repeat for the humidity normal and also for the windy true. And this is the probability of having play yes, and divide by this, and we get this number. This is the probability of um, playing equal to yes given x. Okay, so we will recompute this one, but now we are using the no here. So for the no, we get 0.010. So given that we have two probability, so we choose the higher one, which is this one. So that means our answer for the class will be we will play, because this one given x, the probability of playing is higher. Okay, so this is uh, uh, our conclusion. Since given x, the probability of play is yes, higher compared to the probability of having play no given x, so then we should play. Okay, so if you notice that all of these are in categorical value, so if you have numerical value, so you cannot do that unless if you change them into um, dummy variable, or you can put a range and then you can change them into categories value. Okay, let's take a look at this simple example. So in this example, using the R software, we are going to um, classify spam and non-spam um, text SMS. So on your left-hand side is a sample of non-spam. They call it ham. And then on your right-hand side, we have the spam. So the keyword here is that if you have free, that means that is a spam, but we don't know yet. Okay. So the first step towards constructing our classifier involved processing the row of data. So we need to tokenize all the wood that we have, and then we are looking at bag of woods. So if you remember, we have studied information retrieval, right? So we from the sentence we construct the TF-IDF or bag of woods lah. Frequency. Let me erase this. So basically, we convert them into something like this. Okay, so for each of the SMS here, we compute the frequency of each term that we have in each of the sentence. So this is bag of woods. So from here, we can compute the probability. Okay, so we start from the earliest one. Okay, so let me go to the R software. But I need to get the file first. You're looking at SMS. Which one we're looking at? SMSS. Okay. Okay, so we will get Mm, okay, so we all set. So first I will read my file. So for this one, I'm reading from my Active Directory. So all my string vector to be false means that um, all the string of character will be maintained. Okay, that will not be changed to vector. So if you look at the structure of the SMS here, so we have type and text. So both type and text will be imported as string of character. So if I look at here, so you look at character here. So this is because we put this one as false. Okay. So this is okay, string of character, but this one we need to change into uh, label. So we need to convert into vector later on. Okay. And how do we convert them? So we are saying that, okay, I will take this data set and I focus on this column. I will change them into vector. Okay, so if I look at the structure again, now my type is now vector. Okay, so instead of string of character, I change them into label. Okay, and we look at the number of row that containing ham and spam. So ham here is non-spam SMS. Spam is spam SMS. Okay, so we have imbalanced data here. So this is like 20%. So we will install the text mining uh, tools, and then we upload into memory. Okay, so what happened is that the first step in the processing text data involve creating a corpus. A corpus is a set of document. Okay, so we will convert the text into set of document. So we take each of the text and then we convert into vector, and the vector represent one document. So we have a set of document here. So we have SMS corpus. Okay, and then if you look at the corpus that we have, so we basically have 5,559. So they take this one as one entity, which is set of document. Okay, so we can inspect individual document that we have. So this one is looking at the row number 1 up to 2, the first 2 row in your set of document. Okay, we can also look at the one sentence, but this is as a character. So if you look at, we have this double quote, so string of character. Okay, And we can also repeat this one, means we are applying this function listing all the character for row number 1 up to 3. So 3 rows. Okay, so these are the sample of text SMS that we have. Okay, now we want to clean the data, so we want to remove everything. So if you look at how yeah. So if we look at, okay, this one will clean. So if we repeat, okay, now we have hope and everything can. So this one is too lower. So they will change everything to lower. So if we, oh, this one does not apply. Oh, we looking at this one. So we are looking at that one. We just type it. Okay, so now we compare with the previous one. This is capital H. This is lower H already. Okay, so this one change to lower. So we need to do the rest, like we remove the numbering. So we remove the numbering and see. So we don't have number here, so that's fine. We need to remove the stop word, but it depends on the library. Some of the stop word that we consider stop word, but not for them. So if we, so that means in only all those will be removed. Okay, and then if we remove all the punctuation, okay, so we no longer have the dot here and many more. And now we need to remove the white spaces again. We also have to remove the stemming. No, we perform the stemming where we remove all the ing, s, and so on. Oh, there is no call snowball. We need to install. Um, and we need to upload them into memory. Then we can do the stemming. Okay, so if we look at the list of ni, oh, yeah. So the ing, s also all removed. Okay, and then we also remove all the white spaces. So now we have a complete one. We have cleaned our data. So capital letter, all the white spaces, all the um, stemming. We have done the stemming and also remove all the punctuation. So we have a very clean data here. Okay, and now we want to form them into term document metrics. So this is, we take the clean corpus and then we transform them into document term matrix. So if we look at the content of this, so basically we will see, okay, we have 559 document number of rows, and we have 6,555 number of terms. So the weighting here, we are looking at the frequency of each of the term, okay, TF. So that is the number that we use. Okay, so now we are, since we have them in the term matrix, so now we can say, okay, I'm taking around 80% of them to be in my training. So this is raw number, okay, and then the remaining I will put in the training, the testing. Sorry. So we have two parts. The first one is training, and this is the testing. And then we also take the label for the training and also for the testing. So over here, I'm looking at this data and I'm focusing on the column, and I put in this label, uh, training label and testing label. And if you want to look at the probability of the classes that I have, so we have 85% on the ham and 15% of the spam. So this is for the training, this is for the testing. That's why we have equal number of proportion for ham and spam for both training and testing. Okay, we can visualize the content of each of these by using the word cloud. So we can do visualize the content of each of the SMS that is ham. So this is for the overall, where we only focus on frequency which is 50 and above. Okay, so this is what we get for the whole document. Okay, but if you want to focus on individual one, so we will split them into spam and also ham, and then we can visualize individual set of document. One is, this is for the spam. Okay, so for the spam we have free, call, text, reply, or and so on. This is for the non-spam. So we can look at how they are different in terms of the most frequent term that exists in the SMS text. So this is just visualization. Okay. So now we can look at how do we train the naive bias. Okay, so over here, since we have around how many? 6,550 terms. So sometimes we want to focus on reduced number of dimension. So over here, I want to find frequent pattern from the trend which having at least 5. So we have all this. Okay. So not all we can put in the nil. So what happens is that I will find all the this is for the, I will collect all the term that is frequent. So that means at least 5 times. So I put in this bag of woods. So I say this is the bag of words for the frequent word. So the 5 here is subjective. You can put 10 or 8, but in this example, we assume if the term exists at least 5 times, they are frequent. Okay. So the content of this would be list of word. Okay. So basically, we have around 1,140 only. So from 6,000 something, we reduce to 1,140 to be used. Okay. So we will only use this term. So what happens is that I will only extract this, and I will have um, another set here for my training and also for my testing. So that means I reduce the number of terms that I use. Okay. And then this one is just to count, since um, we are defining a function count here. So if x is greater than 1, then yes. So this is just to, okay. So since the naive bias is highly dependent on the counting, so we have we should change. Okay, the naive bias classifier is typically trained on data with categorical features, so not for numerical values. So this poses a problem since the cell in the sparse metric indicate a count of the times would appear in. Okay, so in this example only, we are looking at because in the back of words that we have is just a number, but we want to change them into categorical value. Okay, so if they are greater than 0, that means they exist. So we just change yes and no. So from number we change to yes and no. Okay, so that is the function that we use. So we will apply that one in both of our training. Okay, so we will apply this one. So if we look at the content, can we see the content? Yes. We only can see this term only for individual term. Yeah, and we will do again for the test here. Because this one's supposed to have more rows, and then the another yes or no, but it's okay. So as you can see here, the result will be two metrics, each with factor type column indicating yes or no for whether each column would appear in the message. So basically what you have here is would, and then follow at the bottom, but it cannot show all of them. So at the bottom you will see yes, no for each of the term that they have. Okay, so having to have that one, so we can use the knife classifier. First we need to install this package and then load into the memory. And in the test here. Okay, so this one is just to plot the table that we have, and so that means this is okay, but we have misclassification for this.
Sorry, Prof. We cannot
Yes.
see slide.
Huh?
We cannot see your slide.
The R software can.
Cannot toh.
Oh, okay. Boleh.
No, slide. Ini slide.
Wait. Ini boleh.
Slide kah, Prof? Kalau sekarang view kami slide.
Iya, slide. Wait. Let me get out from here first. I stop sharing first. I share the entire screen. Now you can see the R Studio.
Yeah, can. Now.
Yeah, Prof.
Okay, so for the ham and ham, that is good. This is good, but we have misclassification for this because the actual label is spam but considered as ham, and also this one. So we have around 36 divided by the total of all this, which is 1390. Okay, so accuracy is around 97.5. Okay lah. Okay, so that's how we use the where am I slide? Okay, so for this one, we have around the total is 95% lah. But if we look at individual classes, we have 0.3% for the uh, non-spam and 15% for the spam. High error for the spam. Okay. We can also build the naive Bayes model as before, but this time we set the Laplace to 1. So we can set in the statement there. Here. So Laplace refer to a number that can vary the distribution of your data. Okay, any question? Okay, so if no question, I let you do that one on your own. Kita punya final exam tu bila tu? Macam